Welcome to the explainer corresponding to the topic, the psychological repeated measures design. I'm going to ask, as usual, questions, and I will ask you to try to answer the questions by going back to the masterclass and see if you know this topic, the answers already. If you don't, then come back and see my answers. Or if you do think you know and you try to answer the questions and you come back and match your answers to my answers. I will start with one question and then I will do a recap of topics not just in the last masterclass but in the last 3 masterclasses. So the first question is, what is the difference between the original Gosset's or student Z-test and the t-test presented by Fisher and attributed to Gosset? So the difference between these two, the original Z-test proposed by Gosset in his paper in 1908 is a Z-score that calculates first in the numerator the mean of different scores minus a population mean of different scores, and that divided by the standard deviation of different scores. Okay, so that was the original Z-score proposed by Gosset, and he developed a sampling distribution of the Z-score and used that sampling distribution to determine the p-value, which we are going to see later. Now, in 1935, Ronald Fisher, in his book The Design of Experiments, proposed the t-score, which is the same as the z-score, but with the addition of dividing by the square root of n, and where n is the number of observations in a sample. So, but Fisher attributed this t-score to Gosset, even though Gosset didn't use it. He used a similar one. And he used the ideas of Gosset, which is, Gosset developed the z-score, but also he developed a sampling distribution of that score. And the way he did it was original. And that way of developing a sampling distribution is what Fisher took from Gosset. He attributed it to Gosset and he developed the t-test, and he said this is Gosset's test. Actually, he used the pseudonym of student. Okay, so and this is the one that we use today and is also attributed to Gosset or student. Okay, so we are going to do a recap of the last 3 statistical masterclasses. And I start with a question, which is, what are the 3 statistical analyses explained so far in these 3 masterclasses? Okay, you need to go to the last 3 masterclasses to try to answer this question. So the 3 analyses that we did were, the first one, comparing a sample with a population. The second one, comparing 2 independent samples. And the third one, comparing 2 paired samples. And the beauty of that is that we can use different versions of the t-test for each of these 3 cases. For the first case, we can use a one sample t-test. We haven't seen this in the master classes, we saw a more rudimentary way of doing the comparison of one sample versus the population. The second, which we did see, which is the independent samples t-test, and the third one, which corresponds to the current masterclass, is the paired samples t-test. So let's see what the characteristics of these tests. So there's one sample t-test. The score has in the numerator mean of a sample, so x bar means the mean of a sample, minus mu, which mu is the Greek letter that we use for the mean of a population. So basically in this case we've got a sample and we want to see whether the sample that we have is different from a population. So this sample came from a specific population, and that population we give it a mean. That's the mu. And what is the population we want to compare with? Well, sometimes it's a population in which the mean is 0, because we want to know whether our mean is different than 0. But most of the cases it would be to a particular mean. Let's say that it is the mean of a distribution of scores in one country, and we get a sample, and we know the mean of that in this score of that country, and they give us a sample of scores. We don't know if it belongs to that country or not. So what we can do is to compare the sample that we have with the mean we know that that country has, and to determine how likely it is that the sample we have corresponds to that country. Now, we can use the normal distribution if we also know the standard deviation of that population. But if we don't know the standard deviation of the population, which is in most cases is the case, and we don't know, then we use the t-test, and we use the t-distribution rather than the normal distribution. So that's the numerator. In the denominator, SEM is the standard error of the mean. And the standard error of the mean is a sampling, so is the standard deviation in a sampling distribution. Okay, so we need to assume that we've got a population in which the mean of that population is mu, the value of mu, which could be 0 or could be a different value. And we extract samples from that population, and we calculate the mean of that sample. We repeat that thousands of times, so now we have thousands of means of those samples. And with that, we generate a distribution of means. The standard deviation of that distribution of means, we call it standard error. So that is the standard error of the mean. Now, then that value t that we obtain for our sample, which tell us how far the mean of our sample is from the mean of the population that we are interested in comparing with. And so the t-score we obtain, we compare with a t-distribution. And what characteristic has this t-distribution? It has degrees of freedom, df, of n minus 1, where n is the size of the sample that we obtain in our study. Why do we do n-1? Well, there are many reasons, but just take this heuristic. How many means we calculated in this sample? 1 mean. So that is what we have to deduct from the number of observations. So if we had 30 participants and we calculated a mean of our sample, then we got 29 degrees of freedom because we because we calculated 1 mean. So that is the heuristic we have to use to determine how many units we subtract from the sample size. Okay, so that is one type of t-test when we've got only one sample and we want to compare with a population. The second t-test is the independent samples t-test. And we use that t-test when we've got two groups of people that were measuring the same thing. And we want to compare whether the differences between these two groups is significant, and it is not just by chance that we obtain this difference. So what we want to compare is the difference between the means we obtain in our sample and to a hypothetical population in which there are no differences. So here mean difference stands for we've got a sample and we've got in that sample two groups of participants, and what we do is we measure some dependent variable and we calculate the mean in each of these groups. So we calculate two means in this case. After calculating the mean, we calculate the difference, and that's the value we have in the numerator, the mean difference. Now, we want to compare that with mu diff, which is the letter Greek mu, stand from some mean in a population. So that is what that population is a population. Imagine that we've got thousands of values or millions, 1,000 million values, and half of those values we call them A and half we call them B to mimic what we did in our study. We had two groups. And if we calculate the mean of the A values and the mean of the B values, the difference between these two means is 0. So we are comparing the difference we obtain in means in our sample with a hypothetical population in which the difference between the two means is 0. So basically here minus mu diff is actually minus 0. So in a sense it's just the difference between the two groups, the difference in means between the two groups that goes in the numerator. In the denominator also goes the standard error. So that repeats in the 3 t-test, goes the standard error. Now it's not a standard error of the mean anymore, it's a standard error of mean difference. So what is this? Well, we have to assume that we've got a population of values in which the mean of the values A and the mean of the values B is the same, so the difference is 0, and we extract samples. And from those samples we calculate the mean of of the values A and the mean of values B, and we obtain the mean difference. So now we've got one mean difference. And we do that thousands of times, so now we are going to have thousands of differences between two means. So, and we can generate a distribution of those, and that distribution has a mean and it has a standard deviation. The standard deviation is what we call the standard error of the mean. Now, the formula here is a bit more complicated. It uses the standard deviations of the two groups in our sample, a combination of those. But the idea is that what it is a standard deviation of that sampling distribution that we have in mind. And when we obtain that t-score, we have to look at this t-score compared to a t-distribution. What characteristics has this distribution? It has degrees of freedom equals n minus 2. So if we have 60 participants and the degrees of freedom there is n minus 2, so is 58. So why do we do minus 2 or not minus 1 like in the previous case? Well, we do minus 2 because we calculated two means. Remember the heuristic for degrees of freedom. We need to check how many means we calculated. So we calculated a mean for one group and a mean for the other group. Therefore, we calculated two means. And that's why we subtract 2 from the total number of participants. Third test is the one that corresponds to the masterclass this week, the paired samples t-test. Now, the paired sample t-test, in a sense, is the same as the one sample t-test. Why is that? Well, look at the formula. The t-score is calculated by obtaining the mean of the different scores. So this is different than what we did with the independent samples t-test. In the paired samples t-test, we've got two samples, but they are paired. Paired in what sense? In the sense that these two values are not independent. What does it mean? Well, it means that the values in the first sample and the values in the second sample have some dependence, come from the same origin, or at least some pairing has been done. So in the case of repeated measures, what it is that the same person was measured in two instances. And we've got a number of participants, and all the participants are measured in two instances. Or it could be the case that we've got two different groups of people, but these people are matched somehow. Like, for example, like in the study of Winch that we presented a while ago, in which the students were matched by having a test of their memory capacity before doing the experiment. And based on that test, they were matched. So couples were generated of students that have the same memory capacity. So that is the pairing. It's either the same person contributing to the two values, or pairs contributing to the two values. Now, when that happens, what we can do is to obtain a difference between the first score and the second score. we cannot do that in the independent samples t-test. Why? Because there is no relationship between the scores in one sample and the other. So we cannot obtain a different score. But we can in this case. And because we can, we obtain a new variable that is called difference scores or difference. And you know what? We can use that new variable as one variable. So we are now in the same situation as the one sample t-test. We've got one sample and we can compare that with the population. What population we want to compare with? A population in which that the mean of that population is 0. So that's why we've got in this numerator the mean of the different scores. So this new variable that we created by subtracting the two values, and then we compare with a mean in a population of different scores in which those different scores, the mean of those different scores is 0. So basically, if we've got values A and values B, but these values are paired, so when we sample, we sample pairs, not individual values, and then we obtain the difference between these scores. And well, we've got those new values, and the mean of these values is 0. So again, because this value is the value, the mu diff is 0, then in a sense it's just having the mean of the different scores. And we divide by the standard error of different scores. So, but this is also the same as the standard error of the mean. So what we do is from the sample in which the difference between pairs of scores, the mean is 0, then we obtain samples, we obtain the different scores, and of those samples of different scores we obtain a mean. And we do that thousands of times, so we've got thousands of means of different scores. So we create a distribution of those means, and that distribution has a standard deviation. Standard deviation of that distribution is called the standard error. And then we compare the t-score we obtain with a t-distribution with degrees of freedom n-1. Why n-1? Because we are using, even though we've got two samples, but because these samples are paired, we were able to create a new variable, and we are using that variable for the analysis. So in that variable for the analysis, we calculate only one mean. Therefore, we do n-1. Okay, so that's enough for the explanation and comparison and similarities and differences between these three types of analysis that are very common in psychological research. Okay, what are the characteristics of the t-distribution and how does it differ from the normal distribution? Okay, so here is the t-distribution. In black, we've got the normal distribution, the one on top. And the other distributions are distributions that are t-distributions with different numbers of degrees of freedom. The one in red is with degrees of freedom of 1. What we can see then is that the similarities with the normal distribution is that the mean of the distribution is 0. In the case, the normal distribution is a standard normal distribution. And it is symmetrical, so the shape of the distribution is the same to the right and to the left of 0. And basically that's the idea. And also similar is that the central values are more probable than the extreme values. Same in the normal distribution as in the t-distribution. What is different is the size of the tail. So in the normal distribution, the values that are around here become very, very, very improbable. Whereas in the t-distribution with 1 degree of freedom, those values still have a decent chance of being observed. So that's why it's a very, very fat tail. Now, when we increase the degrees of freedom, the t-distribution becomes more and more like a normal distribution. So in red is with 1 degree of freedom. Then here is with 4 degrees of freedom. Then 8 degrees of freedom. Then 12 degrees of freedom. So, with 12 is becoming closer and closer to the normal distribution. If we get 30 degrees of freedom, it will be like the normal distribution. And if you keep adding degrees of freedom, still is like the normal distribution. So the t-distribution has values in the extremes are more probable than in the normal, but when you've got a large enough sample, then it becomes like the normal distribution. Another question, what does p-value mean, and what is the difference between 1 tail and 2 tails p-value? Okay, so the p-value is assuming a population in which the null hypothesis is true. And the null hypothesis could be that the difference between two means is 0, that the value of the population is a specific value, or that the difference scores, the mean of the different scores is 0. It doesn't have to be 0. It could be another value, but 0 is a very popular. It's typical to want to compare to 0. Now, if you obtain a sampling distribution from that population, and we use t-scores, so we calculate t-scores and we got a t-distribution. Now, if that is the case, what is the probability of observing the t-score we observed in our study, or a more extreme value? So that is that p is the area under the curve. So in terms of probability theory, probability of observing a something between two values, or an interval of values, we obtain not by looking at the curve itself, but by looking at the area under the curve. So let's say that we consider a t-value of 2, and we are using 1 tail. So p-value means what's the probability of observing 2 or a higher value in that distribution. And depending on that depends on the degrees of freedom. Okay. So what does it mean, 1 tail or 2 tails? So 1 tail has to do with the hypothesis that we generated at the beginning or before running the study. If the hypothesis was that we were going to have the values are going to be higher than 0 in our sample, and that's a directional hypothesis. So we are not saying that the values will be different than 0. We are saying that it is higher than 0. If that was our hypothesis before running the study, then we looked at 1 tail only. So what is 2 tails? the two tails we use the same distribution, but now, and the p-value is the same, but what we consider more extreme changes. So now the more extreme is we have to look at the two sides of the distribution. So again, if the t-value is 2, that obtained in our sample is 2, we look at the area under the curve from 2 to the right, but also we have to add the area under the curve from -2 to the left. Why is that? Well, because we said in our hypothesis that we are going to find values that are different than 0. So it could be negative or could be positive. So when that is the hypothesis, then we need to look at the two tails of the distribution to determine the p-value or the probability. Okay, so in which instances is the paired samples t-test used? Well, so we need to have an independent variable and a dependent variable. The independent variable must be categorical or nominal with 2 values, and the dependent variable a numeric variable. Okay, and we've got cases in which we have paired participants. So we've got one participant and another participant that we pair them we match them based on some skill. They have the same memory capacity. Or age. Let's say we've got large range of ages and we want to pair participants by their age. So we have participants that have the same age. So when that happens, then we use this paired samples t-test. Or the same participants in 2 conditions, or the same participants before intervention and after intervention. So let's say we measure the participants before going through psychotherapy, we measure them in depression, and after going through psychotherapy, we measure them after the intervention in depression, and then we calculate the difference. So these are the main instances in which we use the paired samples t-test. What are order effects and how are they controlled? Okay, so order effects in repeated measures designs are learning and fatigue. Learning, it means that because we are going to expose the same person to 2 measurements, it could be that when we expose them to the second measurement, the person learned from the first exposure. So that's a problem. And before I explain why, I explain the other, which goes in the opposite direction, which is fatigue. The person who was exposed to a measurement gets tired after performing that measurement, and then by the time performing the second measurement, the performance decreases due to being tired. So, what's the problem here? The problem resides on that if we've got condition A presented first and condition B presented second, and we want to compare the difference between A and B, we want to see whether they differ, the difference that we find in our study may be to the difference between the 2 conditions, but it may also be due to differences in learning or to differences in fatigue. So if we observe a decrease in performance in condition B compared to condition A, it may be because condition B is more difficult, but it may be because people got tired. So that is confounding. The variable fatigues and learning are confounders. So how do we solve this problem? So we solve the problem by two ways. One is called counterbalancing and the other one randomization. Counterbalancing is simple. We ask half of the participants to go through, let's say, condition A first and condition B second. And the other half of the participants will go through condition B first and condition A second. So now we don't have that A was performed in all of the participants first and in all of the participants second. So if we find a difference between A and B, it's not due to learning and it's not due to fatigue. If learning and fatigue may still be important and may modify the measurement in the dependent variable, but if we obtain a difference between A and B in the dependent variable, it's not due to learning or fatigue, because the difference between these two groups, because some went before and some did condition A before and some did it after. So there is no more confounding. A different version is randomization. So that's when we have more than one item per condition. Let's say in condition A is solving some reasoning problems with some distraction, and condition B is without distraction, solving the same problems but without distraction. Instead of having one instance of each condition, we may have two problems per condition or more. And what we do is, across the whole sample, we randomize the order of the problems and whether they go through a condition with distraction or without distraction. That is randomized. Rather than we say 50% and 50%, we randomize. We can do that when we have a large sample, because we make sure that the randomization will give 50% of 50%, or in this case it will be being in different orders, not just first and second, because we may have more than two in this case. So the idea of randomization is the same as the counterbalancing, but in a different way. It's avoiding to confound learning and fatigue with the independent variable. So by doing this, we don't eliminate the effect of learning and fatigue on the dependent variable. That still may still happen, but the difference between the two groups will not be explained by learning or fatigue.